Okay, so let's go. Today we're going to cover the next topic, which is linear approximation and marginal analysis. That's 3.2. Which is the last topic we need to know for the next test. It's a very important test for a lot of you because we needed to drop test 1. So that would be the test on calculus, which hopefully you've been doing okay so far. Now, in 3.2, we're going to talk about some applications. Linear approximation is one application. Marginal analysis is another application. Let's start with linear approximation. Here's the idea. I have a function that's doing something, could be doing whatever. This is my f of x. There's some point that I know about this function. Right? Let's call that point A. Right? At that point, I know what f of A is, and I also know the slope of the tangent line at that point. So I know f prime of A. So that point is a nice point. Now there's another point somewhere over here called x. Right? In which case, x is the corresponding y value for x is not known. So let's say the unknown is f of x. Right? So there might be various reasons for why this is not known. One possibility could be the function itself is so complicated that actually computed at x, what the actual output would be very difficult. You probably need some computer crunching numbers for a long time before you can figure it out. Or it could be the fact that the function actually doesn't even exist yet. Right? So it could be a case where we want to predict something in the future. Anyway, so that's the situation. I know everything at this point, but at this point I don't know much. I don't know the slope, I don't know the y value. And the point here is to approximate f of x. Because computing f of x may be difficult or impossible at the moment, and so what we're going to do is we're going to try to estimate it to the best that we can. And one way we do that, it's called linear approximation, right? We're going to approximate it with a straight line. That's why it's called linear, right? So here's the idea. We know the tangent line at that point. So what we're going to do is we're going to think of two things. Remember one thing that a tangent line does is the more you zoom in, the closer it actually gets to that function, right? So notice that over here, the distance between the tangent line and the function is farther, but the closer you get in, the more they align together, right? So the idea is if x and a are close together, the tangent line and the function are actually close together as well. The tangent line, though, I know everything about that. I can find the equation of that because y equals mx plus b, and I know that m comes from the slope at this point, right? So that's a very easy equation to deal with, whereas the function itself might be very complicated, right? So one thing I know, I can actually find the equation of the tangent line, which we've done before, so I'm not going to do it again. It's going to be the y value plus f prime at a times x minus a, right? That's like y1 plus n times x minus x1. Right? So that's going to be the equation of this tangent line at the point x equals a. So here's here's the assumption. When x is close to a, emphasize close, then the y value of the tangent line is close to the y value of the function. And the closer we make x to a, the closer these two will align. That's the property of the tangent line. I.e., the y value of the function at the point is f of x. So what we're saying is when x is close to a, that is nearly the same as, which you write a squiggly equal sign, to the output of the tangent line itself, which is going to be this guy. And that's why it's called a linear approximation. You're approximating the y value using the equation of a straight line, in particular the equation of the tangent line. That formula is called the linear approximation formula. Basically says f of x is nearly equal to f of a plus f prime of a times x minus a. That's called the linear approximation formula. So that's a formula that we just know now. That needs to be memorized. When x is close to a and f is differentiable. So that's basically the idea. That whole argument is just to get to this equation, which is an approximation of our y value, which in general, to find it specifically, might be very difficult. But to find this values, it's going to be a lot easier. Here are some general guidelines. Note. X is the, this is not an official name, but we'll usually think of it as the ugly number. So there's some x value that's usually kind of strange that we want to figure out what is the y value at that value. Second thing, a is a nice value. I shouldn't call these values. We usually call values with the y. Nice number. That's the ugly number and the nice number. That know f of a and f prime of a for. Or we can figure them out with relative ease. So that's the idea. The property, one property of the tangent line is the closer you are to where the tangent line was, the point that the tangent line is fixed to the curve, the closer the curve and the tangent line coincide. So if your x value is close to the a value, the equation of the tangent line is very close to the actual output of the function. This guy might be difficult to compute sometimes, so we can instead use that as an approximation. The closer these two x values are together, the better our approximation is. So this is actually very important. This is one real life example, a real world example of how a derivative is used. Okay. And now for a typical kind of problem that you might see in a 205 class. Very typical. So when I ask you about linear approximation on a test, this is pretty much how it's going to look all the time. On a test and on a final, and it will come on a test, it will be on the final. So let's do that. So the problem would be phrased like this. Use linear approximation to estimate. I believe my first example was the radical of 3.99. Just might take something like that. Right? Very similar wording. Tell you use linear approximation to estimate something. Right? And so this particular function is not a difficult one to deal with, but it's just to show you the idea. In 205, we don't really deal with anything too crazy. Okay. So let me illustrate the steps, and then we'll do another example. Step 1. Set up an appropriate function. Here. So we want to approximate the radical of 3.99. What function do we think we can use to start to figure that out? Take a guess. Huh?
Approximation formula?
No, like the actual f of x that you want to figure this, use to figure that out. What do you think you can use? Huh? 2? 2? Like the function 2? Like this horizontal line?
Exponential.
What kind of exponential?
Increasing.
Well, we have the square root of a number. So what function do you think we should use to figure out the square root of a number?
Natural number.
How can you use a log to figure out the square root of a number? How about we just use the square root of x? That seems right? We want to figure out the square root of something. Hey, use a square root function. Kind of makes sense, right? So that's the first thing. You set up a function that looks like the thing you want to approximate. Now, obviously, our x value here is 3.99. That's what we want to figure out the output for. So that's kind of an ugly number. It would be much nicer if it was a 4, right? 3.99 is kind of ugly. If it was a 4, we'd be done. We didn't have to do anything. So that's the first thing. You set up a function. Step 2, differentiate the function. Why? Because we want to use the equation of the tangent line. We need the derivative in order to find that. So here, we're going to have f prime of x would be equal to
half x.
3.9
f of x is square root of x. What's the derivative?
Half x
half
is
to the negative
negative a half.
Right. 1 over 2 radical x. Step 3. Identify your x and a values. f of a and f prime of a, because that's what we're going to need to plug into that formula. Right? So here, who do you think x would be? Who do you think a would be? Right, the x is 3.99. That's the ugly number that we want to figure out the square root of, right? A is? What?
That's right.
Remember the definitions. What was A?
Nice.
It's a nice number that is? A is a nice number that is close to x, that we already know all the values for. 4. Right? If that was a 4, I know all the values already, right? I wouldn't have to do anything. I don't know what the value is at 3.99, right? So x is that ugly number that I don't know what the square root of 3.99 is, but I do know what the square root of 4 is, and 4 is pretty close to 3.99, right? There are a bunch of other numbers that I know the square root of. I know the square root of 16, but I wouldn't pick 16 because 16 is not close to 3.99. 4 is a lot closer to 3.99. I also know the square root of 1, but 1 is not as close to 3.99 as 4 is, right? You want the number that's the closest to this number that you want to figure out. That's very nice that you know all the values for, right? So now I want to figure out what is my f of a. Well, that's just f of 4, right? Just a is 4. So what is f of 4? 2. F of x is the square root of x. F of 4 is just the square root of 4. That's 2. Now, what is my f prime of a? That's just f prime of 4. One over 2 radical 4, right? Because I know my derivative is 1 over 2 radical x, and I'm plugging in a for that, that's which is 4, so it's going to give me that, which is 1 over 4. Right? Which now brings me to step 4. Plug into the linear approximation formula. To estimate the required f of x. So now I know that f of x is approximately equal to f of a plus f prime of a times x minus a. In other words, what I actually want to figure out, I want to figure out what is f of 3.99. Right? That's the radical of 3.99 is my function. Radical of 3.99 is just f of 3.99. 3.99 is an ugly number though, so I'm going to approximate it with using 4. F of 4 plus f prime of 4 times x would be 3.99 minus 4. So my a is the 4, my a is the 4, my x is 3.99, my a is the 4. My x is 3.99. So I'm simply plugging everything into this formula. F of 3.99 is actually the radical of 3.99, which is what I want to figure out. It's not a nice number, so I'm going to use these numbers to figure it out. So now you start plugging them in. This means the radical of 3.99 is approximately equal to f of 4, but what is that? That is 2. Plus f prime of 4 is 1/4 times 3.99 minus 4 will give me what? Negative? Negative 0.01. Now that, by the way, is just negative 1 over 100. So this is 2 minus 1 over 400, which is, what's that? Huh? 799 over 400. Now that would be your answer, right? So if this were a test, you're done. That's your answer, right? The radical of 3.99 is approximately equal to 799 over 400, right? Now, by the way, I actually plugged that into a calculator so we can see how good this method was in this case. So here's our approximation. Our approximation was 799 over 400. Now it turns out that that guy is 1.9975. So if you divide that, you get 1.9975. The actual answer, if you plug in the square root of 3.99 in your calculators, the actual answer that you get is 1.9974984. Now I didn't even use a calculator to do this. No, Mom, no calculator. But how close was I? Well, up to rounding, I was close to 4 decimal places. I was within 1/10,000th of the answer, which is pretty impressive considering I didn't even use a calculator, right? So it's like this function, the square root of x, I don't know how it behaves precisely at 3.99, but I use a tangent line to approximate it, and in this case, I was good within 4 decimal places when I rounded, which is pretty nice. So that's one of the powers of a tangent line, is to approximate something. Right? So if your function is something that's ugly, you can't really figure out. Screw it, you can figure it out, you can just do it in calculator. In real life, the function would be a lot messier, and we can't really deal with it easily by just plugging it into a calculator. But we can use the tangent line to get something that's close to our answer. And if our answer is not good enough, let's say I want it to be better than 4 decimal places, then I just pick a point that's closer and use the tangent line there, and I can keep getting closer and closer. So that's an example. Here's another one. So here, just say approximate rid of 8.01. Using linear approximation. Okay, go. What do we do? Set up a function. So the first thing I'm going to do is set up a function. F of x equals
Square root of x.
no.
Cube root, sorry.
Cube root. Right? I want to figure out the cube root of something. The cube root function seems to be a nice function to use. Right? 2. Find the derivative. F prime of x is, in this case, right, so I think of this as x to the 1/3, so I can use the power rule, and what do I get? Right, or I can rewrite this as 1 over 3x to the 2/3. So that's my derivative. Third step. Figure out what's my x, what's my a. My x is 8.01. It's the ugly number that I want to figure out what the function is going to give me. A would be here? 8. I need to pick the number, a nice number that's close to this guy that I already know the answer for. I already know the cube root of 8. So 8, and it's pretty close to that. So that seems to be the number I would pick. And so now I'm going to find my f of a and my f prime of a, which is, in other words, this is f of 8 and f prime of 8. F of 8 would be what? 2. This is just the cube root of 8, which I know is the answer, 2. F prime of 8 would be 1 over 3 times 8 to the 2/3. What's that? What's 8 to the 2/3 power?
4.
It's 4. Just 1 over 12. Why is that 4? Right, flower power. Remember that guy? It's 8 to the 2/3. It's the cube root of 8 squared. Flower power. The bottom is the root, the top is the bottom. Right? So that's just 2 squared, which is 4. And so you take 4 times 3, you get 12. So in this case, our f prime of 8 is 1 over 12. So now we can get down to business. This means that the cube root of 8.01, well, that's just f of 8.01. That's not a nice number, so I'm going to approximate that using f of 8 plus f prime of 8 times 8.01 minus 8. So what is that? F of 8. Find it over here. That's 2. Plus f prime of 8. Find it over here. That's 1 over 12. Times 8.01 minus 8. Gives me 0.01. That's 12 plus 0.01 is just 1 over 100. So that's 2 plus 1 over 1200, which is what? It's a plus. 2401 over 1200. Right? And that's your answer. This is just for fun. This is where you'd stop on the test. You wouldn't be able to do this. But your 2401 over 1200, which is your approximation, is actually almost, if I figured out what that is, I would get 2.0008333, and the 3's will repeat forever. That's actually what that is. The actual answer. You plugged it into your calculator. The actual answer would give you is 2.00083,296. That is pretty close, right? Up to rounding, I'm good to 6 decimal places. I'm within a millionth of the actual answer, which is pretty nice. Did it well with the calculator, because I'm just using a tangent line. This is easy to deal with, relatively speaking, compared to dealing with that. fact, there are a lot of systems that would actually use this kind of maneuver. So there are a lot of times when you're even plugging something into a computer that's really complicated, the computer is not going to actually work with the thing that you plugged in. The computer is actually going to figure out a tangent line and use that to approximate it, and it just chooses the tangent line so that it's good up to how many decimal places can fit on the screen, right? Because that's all it can show you anyway. Right? So there are a lot of times when this really cuts down the work for you, even if you're not doing it by hand. Even when you're using the computer, it's actually easier to work with certain things. There are a lot of things in your calculator you wouldn't even realize. When you're plugging it in, the calculator is not actually doing what you're plugging in. It sets up something else that's pretty close to that because it only needs to give you a certain number of decimal places. So that's actually pretty useful. Cuts down on computational time. Is anyone in here like computer science or something? Probably not. You probably need to do 201 for that. Anyway, that's linear approximation. That's it. And that's how the problems will always look. I'm going to ask you to approximate something. You're going to set up your function, find the derivatives, figure out what's the ugly number and the nice number, plug into this formula, and that will give you your approximation. It'll usually be some sort of fraction that you can write out. And, yeah. This you won't know on a test, but I just thought I'd show you that because it's pretty cool how close I can get to the answer without a calculator. At least I think it's cool. Any questions?
Yeah.
Sure. What do you want to approximate? Give me some function.
8.99.
What?
Square root of 8.99.
Approximate the square root of 8.99. Sure. Okay, so what would you say f of x is? The square root of x. That's step 1. Step 2. F prime. If you know that, it's 1 over 2 radical x. Step 3. Figure out who's my x, who's my a. This is 8.99. My a would be 9. Super close to 8.99, and I actually know the answer already. Square root of 9 is actually 3. So now I'm going to find my f of a, my f prime of a. That's just f of 9 and f prime of 9. So f of 9 is I plug in 9 here. That's actually just 3. F prime of 9, plug in 9 here. I get 3 times 2, gives me 1 over 6. And so, my radical, they're all easy when you know the steps. It's just a matter of changing this function. It's the same process for all of them. This is just f of 8.99, but 8.99 is very ugly. I'm not going to use 8.99. I'm going to say that's almost the same as f of 9 plus f prime of 9 times 8.99 minus 9. F of 9 was 3. F prime of 9 was 1 over 6. This would be minus 0.01.
1 over 6
So this is
times
1 over 600. And we know 36 is 18, so that's 1800 minus 1. And so that would be your answer. I don't actually know what that is, but let's see. $1799 divided by 6. This is the 2.99833. Threes repeat forever. The actual answer. Let's see if I can. Do I have the? Yes, I do have the square root. Square root of 8.99. The actual answer is 2.9983328,701. Up to rounding, I'm good to 6 decimal places. or yeah, which is nice. That's it. What's so funny? Guys, always scared. Okay, that's linear approximation. One application of a derivative that's actually used all over the place. In computers, in calculators, computer science. Because even computers don't like calculating difficult, well, it's not that they don't like it, but sometimes calculations compound on each other and it really slows everything down. Sometimes you really want to teach a computer how to approximate something rather than actually compute the actual thing. It's a very useful thing to be able to do. Let's look at another thing, marginal analysis. This is an application in economics. So for those of you who are econ majors, you're going to be doing marginal analysis all the time. And it uses derivatives. So, hey, we're going to do marginal analysis now. So let's talk about what that actually is. It's very similar to a linear approximation, right? We know that f of x is approximately equal to f of a plus f prime of a times x minus a. So this is kind of what your tangent line would look like if you use that definition of derivative when you use the difference quotient that looks like f of b minus f of a over b minus a, right? But for x I put b, right? If I use the f of x plus h notation, then it will look like this. F of x plus h is approximately equal to f of x plus f prime of x times h. All right, so this is using the f of x plus h minus f of x over h definition. This is kind of using the f of b minus f of a over b minus a definition. They're both equivalent, right? But for here, for marginal analysis, they usually use this one. And this is a very important formula, by the way. It's okay for you to memorize that one for linear approximation. Something like this, a lot of you who have to do 209 in the future, you're going to use the equation in this form all the time. Except they're going to use h, they're going to call it delta x. It's exactly the same formula. With exactly the same kind of application. Except you'll be doing it in table form. Yeah. Well, when you get to 209, you'll see. So that's another way to do it. So the idea is the last approximation is best when h is small. Right? So the situation is very similar. It's just a matter of changing notation. So instead I have my tangent line here. I call x the point that I know, and the point that I don't know, x plus h. So this is my f of x plus h. This is my f of x. And so h is the distance between these two, but the closer they are, the better my approximation is. So the smaller h gets to this, is the better my approximation. In fact, remember we get the derivative by making h go to 0. So the thing is, when the distance between these two guys is small, the tangent line and the curve itself are really close together. And so I can use the equation of the tangent line to approximate the y value here. And hence I get this equation. Very similar setup to the last one. Now, in economics e-commerce. And there may be other contexts, but we kind of focus on the economical context here and other contexts. H equals 1 may be considered small. So for example, if our function is tracking, for example, the amount of products that a large producer makes, right? So imagine a producer that produces millions of a product, right? Millions of units, right? Like your Apple producing the iPhone. They create millions of iPhones. Then one iPhone is relatively small in comparison to how many they're producing, right? So that would be super small, right? If my X is like super large in the millions, then 1 is a really small number by comparison. Right? So H equals 1 may be considered small in many contexts. Hence we obtain this guy. Go to here, and I plug in H equals 1. So I get f of x plus 1 is almost the same as f of x plus f prime of x times 1. Or I can rewrite this to solve for the derivative and say the derivative will be almost the same as f of x plus 1 minus f of x. This is a very important. This is a good approximation if your x is large, right? Like it's the amount of products that a very large company is producing, right? Then x is a huge number in which h equals 1 is a very small number, and so we end up with this equation here. So this is basically saying the derivative at the x value is almost the same as f of x plus 1 minus f of x. Now kind of think about what this quantity would represent. Let me give you a specific example so and you can kind of tell me what do you think that expression might represent. Suppose c of x is the cost function to produce x items. Right? So we have a function that describes the cost to produce x units of product. Suppose we're a very big company and we're producing a lot of products. X is large, that's not producing thousands of units or millions of units. Then I'd be able to say that c prime of x is almost the same as c of x plus 1 minus c of x. Now this guy here, how can I interpret that quantity? How do you interpret c of x plus 1 minus c of x, given that c of x is the cost to produce x items?
Cost to produce 1 item.
It's a little more specific than that, but you're on the right track. It is the cost to produce one item, but which one item? The first item, the second item, the third item, the 1000th item? Which item is that talking about? Which item? The what? The large item.
The second item.
Well, let's pretend like X is 1,000, right? So this is the cost to produce 1,000 items, right? This would be the cost to produce 1,001 items. If I take the cost to produce 1,001 items, subtract the cost of producing 1,000 items, which item cost am I talking about? Huh? The last one, the last item, right? Meaning after I produce X items, the cost to produce one more, that additional cost to produce one more, that's this expression. This is the additional cost to produce one more item after X items have been produced. And notice that this thing, this quantity, can be approximated with the derivative at X, right? Meaning, if I produce 1,000 items and I want to know how much more is it going to cost me to make one more item, all I have to do is look at the derivative evaluated at 1,000. And that's going to tell me how much additional cost I would need. So this guy can be thought of the additional cost to produce one more item after I produce some number of items, and it's approximated by the derivative at the X item. Why the fuss? Why use linear approximation? Why can't we just use the function? And why use marginal analysis? Oh, by the way, let me. It's called marginal analysis because this is what happens on the margin, right? I've produced some number of items. So now on the margin, if I produce one more, right, that's like on the outer edge, the margin, right? I can approximate it with this. C prime of X is called the marginal cost function. It is the cost on the margin, right? When I'm on the outer edge of my production line, what are the costs that I'm accruing? So that's the terminology used. Hence, it's called marginal analysis. It's called marginal cost. So if you're ever reading something in economics context and they're talking about the marginal this, the marginal cost, the marginal profit, the marginal revenue, they're actually talking about a derivative, and they're using it to approximate the additional cost to produce one more item. As I said here, function. Why would we go through this fuss? The function may be difficult to work with. Or, and here's where it's really useful, not exist in the first place where we want to approximate it. The marginal cost function is again using a tangent line where we're assuming that the difference between the x values is 1. And linear approximation is like using a tangent line as well. And you might say, why do we need it? Why don't we just use the function that we're given? Well, 1, it might be complicated. 2, it might not even be there. What is the case where it might not even be there? Right, so you could, looking at, let's say the stock market, there's the price of some item that you're tracking, right? And at this point, this is the current point in time. Right? And you know what's going on here. I know the slope there, I know the value there, because I can match it to the price. Let's say this is the price of a stock that I'm tracking, right? So I've been tracking it, okay, I can see how it's behaved, and right now, at this current point in time, I know what's going on. I have all the information. After this point is the future. I can't predict the future. I'm a human being, right? Now, the idea is, the function doesn't even exist over here. I don't know what's going to happen. But I can approximate it if I just want to know what's going to happen in a very small interval of time. In theory, if the interval of time is very small, you don't expect some huge fluctuation. The market isn't going to drop to 0 in the next 2 seconds, right? Or it's not going to shoot up in the next 2 seconds, right? In theory, right? Nothing crazy is going to happen in this interval, but I can get just enough edge to make a bet. I can either know I'm going to buy this stock or I'm going to sell the stock, right? And I just want to know, okay, I'm on the margin, I'm on the edge. What is the decision I'm going to make with this stock? Am I going to buy more or am I going to sell? Do I expect it to decrease or increase? What you're going to do is you're going to set up a tangent line there, and you're going to use the value that the tangent line would be at the future, and you're going to assume, I'm going to assume that that's going to be the value where the stock is going to be. And you're going to make a bet based on that value. Now you might be right, you might be wrong, but it turns out they're more right than wrong usually, right? Because the small time interval, nothing crazy will usually happen in a small time interval. Things will usually go the way they've been trending in a very small amount of time, right? So the whole reason why we might use a tangent line is to just, not just approximate a function, but to predict what I think a function is going to do in a small window of time, which is a very useful thing. And when you look at something like high frequency trading, that's kind of what the computers are doing, right? They're tracking this into some like microseconds, right? Before the market can even move, the computers predict what they think the market's going to do. They buy and sell millions of stock before you at your home clicks to buy the stock, right? So that's how they're always one step ahead of you. They have these really powerful supercomputers doing this analysis all the time in real time. Every time the market moves, creates a tangent line and approximates what's going to happen. Oh, people will tend to buy more and sell more. The computer will just, within some small window of time, right? They're not going to make much difference, but hey, if you do it millions of times by millions of stocks, it adds up, right? And it's going to be doing it in a window that a human being can't compete with, right? And so that's how a lot of people make money, right? So that's why we might want to use linear approximation or marginal analysis. Sometimes the function, we don't even know what it's going to do. The tangent line gives us an approximation. It can predict a future value. Now, it doesn't always work, but it works often enough. The probability of you being correct is actually relatively high. And that's why they do it. It's actually useful. They use it in the real world. So let's actually we're not going to do anything that complicated in 205, of course. Let's look at what a 205 problem would do. I'm not going to figure out what Apple stock is going to do in the next 2 seconds so we can all be there. Okay. Let's actually do, before I give you an example, I'll have to do some more definitions. Okay, so by the way, you can think of marginal as meaning derivative. Right, you can kind of use those words interchangeably. So for example, if C of x is a cost function, then C prime of x is the marginal cost function. Right, or if R of x is revenue, then R prime of x, we call it the marginal derivative. Etc. Right? So marginal means derivative, right? And what the interpretation of that derivative is the additional cost of one more unit. Or this would be the additional revenue if one more unit is produced. Right? So marginal, you can think of it as derivative, and you can interpret the derivative in this context as the addition of one more thing. What will happen if I go one step further? Right? And you also have the idea that I didn't actually do it yet. I want to predict in the future. Like, I know what it is now. What would happen if I did one more, right? So for example, if I'm producing some things and I have this function that tells me my current cost, and I know, okay, if I produce one more unit, what's it going to cost me? And then you can use C prime to approximate that, and then you think of how much profit would I make from that one more unit? And if the cost exceeds the profit, I'm going to be like, no, I'm not going to make one more unit. I'll just stop, right? So you can literally look at the derivative of the function, and once your derivative drops below your profit, that wouldn't make sense to make anymore. So you can actually predict how many units you're going to want to make before you even make them. So it's a very useful thing. So that's a marginal, means derivative, and in marginal analysis, that's the interpretation of the derivative. The additional whatever you'll get by producing one more thing. Right? You can also have profit. These are the typical things talked about in economics. So if you have a profit function, P prime equals the marginal profit function. Right? How much profit will I get if I produce one more thing? D of x is the typical notation for what's called the demand function. It's the function that tracks the price per unit sold. So it tracks the price per unit based on how many units you're selling. Whatever function tracks that, you call it D of x. That's called a demand function. By the way, if I know the demand function, my revenue function is actually equal to x times the demand function. I used that idea when I did the hot dog stand example in lecture 1. And also, the profit function would be equal to the revenue function minus the cost function. Remember, revenue function can be thought of how much money you make for selling X items. Also the cost to make X items. P is your profit. So if I know how much money I'm making and what it's costing me to make those items to make that amount of money, I subtract the two, I get the profit. How I figure out this guy is by taking X times the demand function. The cost function and the demand function, those are things that are computed in real time, right? Here, to figure out the demand function, you're actually tracking the market. So you have to use statistics and probability and all that stuff here. And in the cost function, that's you just doing your books, figuring out how much would it cost me to buy the machines, how much would it cost me for labor, how much would it cost me for this. And you calculate all that, and you can get a function that gives you the cost. Right? Then you track the demand, you multiply it by X, that gives you how much revenue you have, subtract the cost, and that gives you how much profit you're making. And you can always check what's happening on the margins to know if I make one more unit, what's going to happen to my cost, what's going to happen to my revenue, what's going to happen to my profit, right? And you keep going until you stop making money. And that's called marginal analysis. Let's do it. There's an idea of average. Sometimes we like to talk about that. If I talk about average cost, it's just C of X over X. The cost over the total amount of things produced. Similarly, if I talk about average revenue, that's just R of X over X, etc. Right? Average, just think of taking the function, dividing by X. What else do we need to know? Don't think you need to know that. Don't think you need to know that. Okay, now let's do it. We have time. Suppose C of Q equals 73 plus 0.6Q plus 0.004Q squared is the cost in thousands of dollars to produce a few tons of copper. So you're a copper mining company, and you figured out somehow that the cost to produce Q tons of copper in thousands of dollars is given by this function. A. What is the average cost function? So I want to figure out how much is it costing me on average to produce each ton. What function would give me that? D. Find the marginal cost function. C. What is the average cost to produce 150 tons of copper? D. Find C prime of 150. What does this mean? Meaning, give me an interpretation of that in words. It's it. That's the problem. So I'm given a function that tracks the cost to produce Q tons of copper in thousands of dollars. Let's start with A. What would be our average cost function? How do we find average cost? Okay, so what is the top here? We have Q over Q, which is going to be what? 73 over Q plus 0.6 Q over Q plus 0.004 Q squared over Q. That's our average cost function. B. Find the marginal cost function. How do I find marginal cost? Huh? It's derivative. That just means C prime of Q, which is? What? 0.6 plus 0.008 Q. That's your marginal cost function. C. Average cost for 150 tons. What do I do? Just plug it into that function. All right, so that says 73 divided by 150 plus 0.6 plus 0.004 times 150. And test either this will be very nice, or you can leave your answer like that. But let me actually just, for the sake of clarity, actually figure out what that is. 73 divided by 150 plus 6 plus 0.004 times 150. So I get 1.6866, and it kind of continues forever. Right, so basically this average cost would be $1,687 on average, right? So per ton, if I produce 150 tons, per ton, I'm spending about $1,600 to produce each ton.
Jhevon,
Yes.
for the average cost, the function is CQ over Q.
Yes, this one.
Shouldn't it be plus Q squared?
What? Where? Here?
Yeah.
No, it's not squared, because I divide all of this by Q. Divide by Q. So this is divided by Q, this divided by Q, Q cancelled, this is divided by Q, Q squared cancelled. So I have the average cost function here. I just plug in 150 here. That gives me the average cost, right? So per ton, I'm paying $1,687. Which means if I'm selling each ton, I better be selling it for more than that to be making any money. Anyway, let's move on. D. Now this asks me to compute C prime of 150. Okay? Now that would be, I'm just going to plug in 150 into this function. 0.6 plus 0.008 times 150.
You said we could leave it like that, right?
Yeah. Or I'll give you something nicer on the test, either way. So let's say I did 0.008 times 150. Here I get 1.8. Which means this is kind of equivalent to $1,800. Okay, so find C prime of 150. What does this mean? What does that number mean? How can I interpret that number? What is it telling me? C prime of 150 is what?
Additional costs.
This is the additional cost to produce what?
1 more unit. 100.
To produce the 151st ton. Right? So if I produce 150 tons of copper, then to produce one more, let's produce 151 tons, it will cost me an extra of $1,800 to do that. By the way, what is the cost for the first ton? So it says, how does this compare to the first ton of copper extracted? What was the cost for the first ton of copper that I dug out? How would I figure that out?
Use the average cost. We didn't divide the average cost.
Well, I mean, I only have one thing, so the average cost is not.
What profit?
I'll just use the cost for the first thing, right? The cost for one item, right? Which is going to be 73 plus 0.6 times 1 plus 0.004 times 1 squared. That's going to be 73.604. In other words, that's $73,604 to get the first ton of copper out the ground. So how does it compare? By the time I get to the 151st ton, it's a lot cheaper. 151st ton is a lot cheaper. Does that actually make any sense? Does that make sense for that to happen? Yes.
What formula did you use to find the cost for the first one?
The cost function.
The verbal.
Yeah, there's a very first function I wrote was the cost function. It was the cost to produce some number of tons. So to produce the first ton is just the cost function evaluated out only. So to produce the first ton, it cost me $73,604. To produce one more ton after I've produced 150, it only cost me $1,800. Does that even make sense?
Change the prices.
That is actually pretty realistic. Because you have to remember, the cost of the first ton, that would include a lot of things. That would include labor costs, the cost of machinery, the cost of a lot of stuff, right? There are a lot of things that you would pay in the first place that once you've paid it, you don't really have to pay for it again, right? Like if I buy the machinery to produce 1 ton, I don't have to buy all new machinery again to produce the second ton, right? Because things will be more efficient as in the long run, right? So if I'm working at McDonald's and I hire somebody to produce the first Big Mac, it costs me a lot, relatively speaking. But once I hire that person and they're working an 8-hour shift, they can make hundreds of Big Macs, right? The cost I would pay per Big Mac is going to be less because I already paid for the person to be there in the first place, right? I don't have to pay for that over and over again, right? So there are a lot of times when in the beginning, your costs will be greater, but as time goes on average, it will start to fall down. Right? But there is going to come a point where you'll realize that the cost you're getting to produce extra is going to be too much based on the amount of profit you're projected to make and all that stuff, and you can just stop. But anyway, that's a typical question here. I guess we'll stop there. It's a long night to jump into a whole new topic. But that's all the material needed for the test, which I think is, weak. So hopefully you start